Engineers just created motors using carbon threads thinner than DNA. In tests, the carbon coil weighed over 80% less than the copper equivalent, cutting a motor's coil weight dramatically. For over 100 years, every electric motor has relied on heavy copper coils. Now, scientists have found a way to replace all that metal with carbon nanotubes that are stronger than steel and carry electricity almost as well as copper, though with some trade-offs in raw conductivity. These motors can bend, flex, and move in ways metal motors never could. This changes everything from electric vehicles to robotic limbs. Here's the science behind this incredible breakthrough and what it means for everyday technology. But first, there's something about traditional motors that engineers have been dealing with for decades. Every motor in the world shares a secret weakness, one engineers have tolerated for over a century. Imagine copper coils heavy and rigid, wrapped around metal cores to create the magnetic fields that power everything from cars to computer fans. When electricity flows, these copper wires generate magnetic forces that push and pull, spinning the motor shaft. But here's the problem no one talks about. Copper is incredibly heavy. Electric vehicles are burdened by hundreds of pounds of copper in their motors and wiring. This weight sits at the very heart of every motor, making the entire system heavier than necessary. This weight triggers a chain reaction. EV engineers constantly battle between motor power and battery life. Every extra pound of copper forces compromises on range or battery size, draining batteries faster. Drone manufacturers face even tougher trade-offs. Half a racing drone's motor weight comes from copper windings. Cutting that in half could double flight time or payload. Medical device companies also struggle as heavy, rigid copper coils limit the precision of robotic surgical arms. Winding these copper wires requires expensive, precise equipment, and fluctuating copper costs add up. Engineers must painstakingly wind thousands of feet of thin wire with perfect precision. One loose wire can ruin the entire motor. Copper's rigidity also locks engineers into rigid designs. It demands heavy cooling due to resistance, limiting innovation. Designers can't create motors for curved or flexible applications. The rigid copper dictates equally rigid, boxy structures around it. Manufacturing costs keep climbing with copper prices. Pure copper is expensive, but precision motor-grade wire costs even more after processing. A single EV motor uses over $60 worth of copper wire, not counting labor. For decades, engineers have sought an alternative. What if a material could conduct electricity without these drawbacks? What if motors could be lightweight, flexible, and efficient without sacrificing power? Scientists have finally found something almost impossibly small, yet incredibly powerful. Carbon nanotubes that are so small, millions could fit inside a human hair. Think of them as rolled-up sheets of chicken wire, except the wire is made from carbon atoms, arranged in perfect hexagonal patterns. Each tube measures just a few atoms wide, making them thinner than DNA strands. Here's what makes this seem impossible. Something this small should be weak and fragile. Instead, carbon nanotubes are stronger than steel. The carbon atoms lock together in tight hexagonal patterns that create incredible strength. A single nanotube can support a weight thousands of times heavier than itself without breaking. The atoms arrange themselves like a perfect honeycomb structure, rolled into a cylinder. Each carbon atom bonds with 3 neighbors, creating a network that distributes stress evenly across the entire tube. This atomic arrangement makes nanotubes not just strong but also excellent at conducting electricity. Electrons can zip through these carbon highways almost as easily as they move through copper wires. Creating useful cables from these tiny tubes requires a breakthrough manufacturing process called lyotropic liquid crystal-assisted surface texturing. Researchers suspend nanotubes in a special liquid crystal mixture that lines them up like combing tangled hair, creating tightly packed bundles for a flexible, conductive core. Engineers then wrap this core with a protective outer sheath that provides structure and flexibility. The result is something called a core sheath composite electric cable. These cables behave differently than anything engineers have worked with before. Regular copper wires break when bent too far or stretched too much. Carbon nanotube cables can bend, twist, and stretch while still carrying electricity perfectly. This flexibility opens up completely new possibilities for motor design.